Hey, deep diver. Ever try to wrap your head around what's going on deep inside, like way down at the smallest level of the materials we see every single day?
It's a whole different world down there.
It really is, and that's where quantum mechanics takes over.
Yeah.
And that is exactly where we are headed on today's deep dive.
Oh, this is going to be good.
We are tackling the Fermi Hubbard model. It sounds intimidating, I know, but stick with us.
We'll break it down.
This model, it's how scientists are trying to predict how materials behave, especially when things get extreme, crazy hot or insanely cold.
And it's not just theoretical. This stuff has huge implications for developing new materials.
Absolutely. And to guide us through all of this, we've got expert speaker here, ready to unpack some seriously cool research that uses something called variational quantum algorithms.
Quantum algorithms, yeah. They're like these specialized tools that are helping us unlock the secrets of this model.
I am so ready. Let's do it. So, first things first. What exactly is the Fermi Hubbard model? Expert speaker, what are we talking about here?
Okay, so imagine like a grid, right?
Yeah.
But it's microscopic.
Okay.
And on this grid, you've got electrons living there. It's like a tiny little city.
I like it. Our electron city.
Exactly. The Fermi Hubbard model is what helps us understand how all those electrons in that city interact.
Yeah.
Because they're constantly pushing each other away, kind of like, those neighbors who always have their music blasting.
Okay, I'm picturing it. So we've got all these electrons. They're like our city dwellers living on this grid. But what makes it so hard to figure out how this whole electron city behaves, especially when we start messing with the temperature?
Well, think about it. As the temperature goes up, those electrons, they get way more energetic. They're zipping around.
Rush hour in electron city.
Exactly. And all those interactions, they just get super complex. Traditional computer models, they hit a wall because it's just too much to keep track of.
So it's like those models, they just can't handle rush hour in a quantum city.
It's kind of like that. And it gets even more complicated when you add in something called chemical potential.
Okay, chemical potential. That sounds a little intimidating.
It's really not that bad. Think of it as the pressure on the electrons in our city. The higher the chemical potential, the more those electrons want to move and interact.
So more pressure, more chaos. No wonder those traditional models struggle. So is that where these quantum computers step in? They can handle the pressure.
Exactly. They're like the supercomputers that can actually keep up with all the craziness happening in our quantum city.
What makes them so different from our everyday computers, the ones we're used to?
Well, it all comes down to how they operate. Quantum computers, they use the principles of quantum mechanics, which is a whole other way of looking at how things work at that tiny scale. Instead of bits, which are like a light switch on or off, 0 or 1, they use qubits.
Okay, I've heard of these. Qubits are weird, right?
They're definitely different. Qubits can be both 0 and 1 at the same time. It's called superposition.
Mind-blowing. So that's how they can tackle these super complex problems. But how are researchers actually using them to, crack the code of the Fermi Hubbard model?
So they've developed this quantum algorithm called qVQT.
Catchy name.
Right. Think of it as a custom tool, built specifically to measure the energy buzzing around our electron city at different temperatures.
Okay, I'm following so far. We've got our quantum city, our superpowered quantum computer, and our qVQT algorithm. How does it all come together? How does this algorithm actually work?
Here's where it gets even cooler. They don't just use one quantum circuit, they use two.
Two. Why two?
Because it's a team effort.
Yeah.
And each circuit has its own job to do.
Division of labor, even in the quantum world. I like it. So what do these two circuits actually do?
Okay, so the first circuit, we call it the state preparation circuit, and it's kind of like creating a blueprint of our city. It maps out all the possible arrangements of those electrons.
So it's figuring out all the different ways our electron neighbors could be hanging out.
Exactly. Now, the second circuit, we call that the energy measurement circuit, and its job is to calculate the energy of each of those arrangements.
So it's like once we know how the electrons are arranged, this second circuit tells us how much energy the whole system has.
You got it. The goal is to find that sweet spot configuration, the arrangement with the absolute lowest free energy.
Free energy, that sounds familiar from like high school chemistry class.
Right.
But remind me, what does it mean in this context?
It's all about balance. It's the balance between the energy of those electron interactions and the entropy of the system, which is like a measure of disorder.
Gotcha. So lower free energy means a more stable, more likely configuration, right?
Right. So they put this qVQT algorithm to the test, and they started with a simplified model, a four-site system, kind of like a tiny electron village.
A good starting point. And did it work? Were they able to create that energy map?
No.
You left us hanging. What were the results? Did it work?
At lower temperatures, it worked beautifully. The qVQT algorithm, using those two circuits, yeah, it accurately mapped out the energy landscape of that four-side electron system.
Okay, but I'm sensing a but coming, lower temperatures, so not the high temperatures that were giving those traditional models so much trouble.
You're picking up what I'm putting down. You're right. When we turned up the heat in the simulation, the qVQT algorithm's accuracy, it did start to slip a bit.
So even with these incredible quantum tools, those high temperature mysteries are still, well, a bit of a mystery.
Yeah, the quantum world at high temperatures, it's a wild place. It's really hard to get a clear picture of what's going on.
Why is that? What makes it so much harder to model these systems when things heat up?
Well, it's a few things. One thing is that quantum computers, as amazing as they are, they're still kind of in their early stages.
So we're basically trying to run super advanced simulations on the equivalent of like an early computer, right?
It's kind of like that. And then there's also just this immense number of possibilities to sort through. Even for a quantum computer, finding the absolute lowest free energy state, the best solution out of all the possible electron arrangements, that's a huge computational challenge.
So it's not just about having a fast computer. It's also about finding a needle in an astronomical haystack.
That's a good way to put it. And the haystack is enormous. That's why we need even more sophisticated algorithms, ones that can efficiently search through all those possibilities and zero in on the most likely solutions.
It sounds like this research is really pushing the limits of what we can do with quantum computers. But even with these challenges, what does this work tell us about the future of designing new materials using quantum computers?
This research is really exciting because it's giving us a glimpse of what might be possible. Imagine, in the future, being able to design materials with completely unheard of properties, all thanks to our understanding of quantum mechanics.
Okay, so we're talking about like the future of materials, right? Stuff that seems like science fiction today. But how do we get there? How do we go from these simulations to actually creating these amazing materials in the real world?
That's the big question, isn't it? It's one thing to understand how something works in theory, but actually putting that knowledge to use, that's where things get really tricky.
So what's the missing link? What needs to happen to bridge that gap between simulation and, I don't know, like real world applications?
It's a lot of things working together. For one, we need those quantum computers to keep getting better, more powerful, and less prone to errors. But it's more than just brute computing power. We also need even smarter algorithms.
So it's like having a super fast car, but you also need a really good map to get where you're going.
Exactly. We need algorithms that are tailored to solve specific problems in material science. It's like we're building this amazing telescope to look into the quantum world, but then we also need the tools to understand what we're seeing.
So we're explorers charting new territory here. What are some of the areas where you think this kind of quantum-enhanced materials design could have the biggest impact? What are we most excited about?
Oh, wow, the possibilities are huge. Think about medicine. Imagine designing drugs at the molecular level with incredible precision, creating treatments that are tailored to an individual's genes. Or how about energy? What if we could develop solar cells that are so efficient they capture almost every single photon of light?
Okay, now that would be game-changing.
Right. And then there's the holy grail of material science.
Mhm.
High-temperature superconductors.
Superconductors, that's conducting electricity with zero resistance, right?
Exactly. Imagine a world where we can transmit power with almost no energy loss. That would be transformative.
Absolutely mind-blowing. So, to wrap things up for our deep divers out there, what's the one big takeaway from our deep dive into the world of quantum materials?
We're really at the edge of a revolution in material science. With these quantum tools, we're gaining this incredible understanding of how matter behaves at its most fundamental level. It's challenging, for sure, but the opportunities are just incredible.
It's like we've been given this glimpse into a universe of possibilities. So, deep diver, as you go about your day, think about this. What if those everyday materials around you could be even stronger, lighter, more efficient? What if they could help us solve some of the world's biggest problems, like climate change or disease? The answers, well, they might just be hidden in the quantum world. Keep those questions bubbling, and until next time, thanks for taking this deep dive with us.